Welcome to our presentation on monitoring and measuring IP media networks from Mike Waidson, application engineer at Tektronix. For the first time this showcase, we have somebody bringing props on stage, so enjoy. And over to you, Mike.
Thank you. I thought I'd start with a few props, so we'll use these as we go along. So we're going to look at monitoring the media network. So that includes looking at standards like SMPTE 2110-20 for video. We're going to be looking at audio in SMPTE 2110-30. And for data, we're using SMPTE 2110-40. So each of these particular streams needs an IP address. It needs to flow across the network and then come to the end device. And to time it all together, we're going to be using SMPTE 2059-2 as the PTP profile. So we'll send that data across the network as well, and hopefully everything will come to the end device and be timed together. When you're looking at these three flows throughout the network, it's a good idea to come up with some kind of strategy as to what you should use for the various multicast addresses, the port number, the payload type. So in each of these cases, you could think of something that would be useful to make it easy for you to identify which is video, which is audio, and which is data. So here at the interop, we chose this kind of strategy. So a .20 indicates that this is a video stream, fairly simple, and it's at the port 5020. And we chose a payload type which can range between 96 to 127. So we chose 96 for video. Then we chose .30 for our audio and a 5030 as our port number. So now we have multiple ways to identify the difference between video and audio. And we'll do the same thing for data, a .40 or a 50,040 port number for that data. And we'll use a payload type of 100. We didn't use 98 and 99 because those payload types are used in 2022-6. So we kind of moved away from those. You could also choose 100, 101, and 102. You get to choose, but you need to come up with some kind of strategy that will help you to identify the difference between video, audio, and data flows that are going across your network, because that'll help you when you try to identify particular flows that are moving around the media network. So you need to think about this, but just on a caution, not everybody should use .20, .30, and .40, because then there might be security concerns if everybody is using the same numbers. So you get a choice. There's three different ways to identify the stream, and you should choose one of those types or multiple of those types in order to identify the stream. When we're looking at the system, it's important to start with troubleshooting the basics, and that's where the props come in. Okay, because we need to be able to check the different types of cable. So we want to use multimode cable maybe in our system. It's got a transmitter and it's got a receiver that are going to go into this SFP. So it's important that these two particular ends of the cable are not swapped. Maybe some people might try to do that as a practical joke or a little bit of fun, right? But it's important to check those kind of cables. And whether you're using single mode or in this aqua-colored cable, multi-mode, like we do mostly here at the interop. You need to check the type of SFP that you're going to use. There are hundreds of these different types of devices, and you can have them as 1G. So if you try and put 10G into a 1G SFP, it won't work. But can anybody read that writing and help me identify which one is which, right? Okay, so this one actually doesn't have anything that indicates that it is a 10G. It doesn't have anything indicate that it is 850 or 1310 nanometers. it has a number on it that identifies it as a product. So you have to go to the website and look up that number to identify that this one is a 1G/10G 850 nanometer SFP. In some cases, you might be lucky to look at this other type I might have in my pocket here. Oops. Let's go back a bit. I knew when I get to having props that would be a difficult, challenging thing to do. But this SFP, actually, if you can read it from back there, it actually tells me that this one is 10G, and this is 850 nanometers. So that's a little bit more easier to read than the other one, which just has a little label. Yeah, you can pass it around. I'd like it back at the end, please. So in these cases, it's important, you can pass that around as well. And so it's important to identify the right kind of cables, the right kind of SFPs, and then once these things are plumbed together into your switch, you've got to make sure that the actual port lights up. So you want to make sure that you get a green light to show that your port is active and not a non-illuminated port, or a port that is yellow that shows, well, there's an SFP in there, there's a cable in there, but there's no connection at the other end of the system. So these are all the basic kind of things that are completely different from dealing with things like SDI, but they are sometimes overlooked. And then you find out that you got the wrong SFP in this particular connection, and somebody kindly inserted a 1310 nanometer SFP when all of your system is 850. So those are important things to check and ensure within the basics. Once you've got a connection and made a connection, within the Prism, it's important to be able to look at all of this kind of data. And there's a wide variety of information that helps you identify whether this is a video stream, an audio stream, or it might be even PTP data. So PTP data comes on a multicast address of 224.0.1.129, and it's shown right here. We also show the bit rate. So if it's video, it's going to be maybe a gigabit or so. If it's audio, it can vary from about 2 megabits to maybe 24 megabits. And the number of channels will increase as that bit rate increases. So you can usually tell that if you see about 9.6 megabits of data, that's usually an indication you have about 8 channels of audio in your 2110-30 stream. Also, you can see the payload type. So we mentioned that you have a variety of different things you can change. And in 2110, that payload type can be any value you choose between 96 to 127. So it's important to be able to check that value to see what you're using for your video, audio, and data streams. Then you must also be able to check the MAC addresses, the source addresses within the system, so you can see what those values are. And each manufacturer has its own specific OUI that helps you to identify what these values are. So 08001111 tells me that's a Tektronix device. The PTP domain is another important part. So that's a logical grouping of all devices together. And you have to come up with an idea of what your domain value should be. So we chose 127 in this particular case. If you switch on a device and it powers up with domain 0, it's not going to see domain 127. So you'll have to go into that device, change its configuration so it's standardized on the value of 127. And for PTP domain, you can choose a value for your system anywhere between 0 to 127. Also in this system, we'll show the sequence errors that might be present within the stream. We'll calculate the value for the RTP clock. So the RTP clock for video should be 90 kilohertz, and the RTP clock for audio might be 48 kilohertz. So you can easily see those values. And we'll also tell you the marker bit frequency. So that's the periodicity of the frame rate, effectively. So this is 59.94. So all that information you can gather from the IP status within this particular flow that's being sent in this pipe. You can also then look further down into the syntax information within the IP layer. So we can look at the layer 5, which contains the real-time protocol. And within that real-time protocol, we have the marker bit. So that's the indication of the next frame. So when the last frame ends, we get a marker bit, and that's an indication that we're starting to start the next particular payload of the frame. Then we've got the payload type, which can range between 96 to 127. You can choose that value, or it might be specific to the device that you're using. So it's important to be able to identify that within the stream. Then you've got the sequence number. So every packet that comes through from the sender to the receiver should increment one by one the sequence number. So we can see that rolling by. If the sequence number is out of order or it's static, that's going to be a problem. And so we'll indicate that in red. We'll also show you the timestamp that's embedded relative to the PTP clock. So in this particular place, we should look at all of this information to see that we can actually be able to decode the video and the audio. In the case of sending these packets across the network, the sender is going to put out these specific packets one after the other, and hopefully they might be equally spaced. That's going to be dependent upon how the sender is able to process those packets. Some may be linear, some may be gapped, some may be a wide distribution for those packets. It depends on the sender that's providing that information that will then embed the timestamp and the sequence number incrementally for each of the packets. Those will go across our network cloud to our end device. Sometimes those packets will take different paths from particular one location to another. So if you came on the bus this morning, you might have gone one way to arrive at this destination here at the NAB show. Other people could have taken a different bus, and it might have gone on a different path. That's what's going to happen to the packets within the network. So not all the packets may arrive at the right equally spaced time because they've gone across different parts of the network. Also, some packets may arrive out of order because they took a longer distance to get to our receiver. So we might have different times between those packets, and we might now get packets that are out of order. So this particular process can cause jitter and out of order packets in our receiver. To look at that information, we should look at the packet interval arrival time. So this is where we take the information and we timestamp it inside the device, and we then see when those packets actually arrive. And that helps us to determine whether we've got packets that are out of order and that we can reconstruct those sequence errors. So in this particular case, you can see the sequence error, RTP, and we've got no sequence errors. So every packet came incrementally, one after the other. If there were any errors, the buffer inside the receiver can actually be able to change some of those orders around, provided it's within the limitations of the buffer. In that case, we would be able to reconstruct the path. In this case, because there's no errors in the RTP sequence, we're good, and we can reconstruct the packet-by-packet process within this system. Another way to look at that data is to actually characterize it within a histogram. So there are different types of devices that send packets at certain times or have a distribution to the way in which they send packets. So in these cases, each device will have a characteristic signature. So there'll be narrow devices which will send packets fairly linearly, one after the other. There'll be devices that will be gapped or wide. So in a gapped particular piece, that's an internet IP gateway card that's taking SDI in and then going to produce packets. In its case, it's going to send packets for the majority of time, one after the other. But when it gets to the end of the frame, it's going to have to wait. It's going to have to wait for the next picture to come by. And so that leaves a large gap. And that gap is then here when the first packet gets sent again for the next frame. And then because the packets are all relatively close together, it'll come back to this part of the histogram. So this kind of structure is what you get from an IP gateway card that is using a conversion of SDI to IP. This one is actually progressive because there's only one particular pulse. If it was interlace, you'd actually get two pulses slightly close together over here. In this case, we've got a wide device that's sending out packets. This is coming from a server. The server is reading the data from a hard drive, it's processing that data, and then it's packetizing it and sending it out. It's dependent upon the server and the processor inside there to send those packets out. So those packets may not be as linear as you expect, and there can be a quite wide deviation between those. So different types of receiver will have to handle this kind of buffer differently than the gapped or linear responses. To understand the timing of the RTP packets, PTP is the cornerstone of that process, and it provides us with a reference clock. From that PTP reference clock, which was synchronized from the Big Bang of SMPTE epoch in 1970, January the 1st at midnight, we've been counting time in seconds and nanoseconds. And we can take that time and count how many NTSC frames have been since then to now, and how many 90 kilohertz clocks there have been since then to now. And that will basically give us a sampled value of that we can add as our RTP value for the datagram. So this provides us with our timestamp for both the video and the audio, except in audio, we might do it at 48 kilohertz clock instead of 90 kilohertz for our video stream. This is very similar to what we might have done with MPEG and our PCR clock. So there's a lot of corollary to that kind of process within our RTP timestamps. What it actually looks like when you look at the data, to give you an idea, this is a video stream, and I've just parsed certain of the data so that you can see the line numbers of this particular frame. When we get to the end of the frame, you can see the marker bit value changes from a 0 to a 1. So that's the indication that we're ending one frame and we're going to start the next one. You can see the sequence numbers increment packet by packet incrementally over time. You can see the timestamp value is the same across all of the frame or the field. It only changes to a new value when you go to the next frame. You can see the extended sequence number will only increment when it goes and cycles through all of the sequence number values that are available. So in this way, you can see how that data is put into the packets within this process and how we can establish the difference between one frame and the next frame and how we sequentially have all of those packets going through the system. Typically in this case, we're going to use PTP to synchronize the system. So in the monitoring device, we're going to synchronize to PTP. So this will act as an end device. Once we're synchronized to PTP, we can compare that to the IP input. So just like we would do for SDI with analog blackburst and our SDI input, we can compare the timing. So we will then see if this value is in the center. Typically, the way we've displayed this at the moment is we still include the line offset. So the start of the actual picture, because we don't send any blanking information, starts at the first picture on the first pixel of that frame. So that would typically be either 21 lines for an interlace signal or 42 lines for a progressive signal, as in this case. So you'll see a slight offset. You'll also see this timing display wander slightly backwards and forwards relative in time, but it's locked. Another way to look at it is we can also take an analog reference and compare its time from our sync pulse generator to the PTP. And those should be in time and synchronized together. And you can get all of the data related to PTP shown within the IP session display that allows us to see the grandmaster ID, the domain number, and the number of messages that we're sending and receiving over the PTP. So that's how we can synchronize our video within the system to PTP. As we mentioned, the RTP value is used to be able to provide us with timestamps. So we can get stream timing information by using both PTP and the RTP timestamps. And in those particular cases, we can plot the received information. So we'll look at video to PTP offset as the timing of the video as it's received against PTP. And then we'll get the timing of the video as it's relative to the embedded RTP timestamps. By looking at the difference between the two graphs, we can see if the device was correctly timestamping the information in the first place as it's sent out, that in those cases, when we receive it back, this will show the difference it's taken for the packets to go across the network. So you'll be able to establish what the network delay is from the sender to the receiver by using this information. Just like in MPEG, we have a variety of different models for the buffer of the device because we have these different kinds of senders. We have linear senders, we have gapped senders, and we have wide senders. And it's going to depend on whether the buffer in your receiver will be able to cope with those particular processes. So in SMPTE 2110-21, there are buffer models describing this network compatibility model for a sender. So this is a sender. Imagine this is a leaky bucket, and the packets are going into the bucket, and they're draining out at a fairly constant rate. What we want to make sure is that in these cases, we have a fairly good medium buffer, so we can drain in, and we don't overfill and go above the Cmax value, which would cause us to lose packets. So we should have a fairly constant drain rate, and we should be able to just put packets in here. Now, in the model for the sender, it is possible that the bucket may be empty. In other words, there are no packets like in the gapped particular process. We've drained all the packets out during the gap, and the bucket would be empty until we start the next frame, and then it would start to drain packets out again. So in this particular case, you could have an empty bucket within this process. The other model is the receiver buffer model. So in this case, we got the same kind of particular process, except this is how we would deal with it in the virtual case of receiving the packets. So there's a process which is designed in SMPTE 2110-21 that provides this process. And we have a packet read schedule that we would ideally set for how we standardize this process. And that process is standardized by these kind of metrics for a narrow, wide, or narrow linear device. So typically what I would do is use the histogram that we saw earlier and be able to show whether it was a linear device, whether it was a gap device, or a wide sender. And we would set our packet read schedule appropriately for those so that it would use these different metrics for the measurement. And then when we look at those particular values, we would then see whether they fall within the limits as we plot the Cmax and the VRX buffer values. So the question here is, do we have a problem within this system? So if you look at this particular process, within the Cmax value, it says gapped. So that's what we have set up for the packet read schedule, in this case for the input. But if we look at the histogram in this case, you can see that this is not a gapped response because that would be a pulse here and some pulse later on. It's actually a wide sender. So in this case, we would need to change this PRS value to wide in order to correctly identify these particular process. So we don't have a problem. The values are still within limits. We just need to change the scale which we're using in this case in order to meet the requirements for our wide linear sender rather than our gapped mode in this particular case. And that's why it's important to be able to look at the histogram when you set up this configuration for your Cmax and VRX buffer. So that brings me to the end of this particular part of the presentation. If you've got any questions, we can perhaps ask those.
Okay, let's have some questions. Anybody? So, what do you think is going to be the biggest piece of equipment that people are going to want that doesn't exist yet for testing or software?
So software. So there's so many different things that can be configured that there are a variety of different things, from the simplest being able to connect all of the devices together. So at this moment, I would say connectivity and being able to identify IP addresses and those processes is important. It's a cumbersome process because you have to know the values, you have to create spreadsheets or other ways to manage all of your IP addresses. And so it's important that there's more devices that become available to support NMOS, ISO 4 and ISO 5 that will simplify some of those processes that the typical operator is not used to dealing with when it comes to IP. They're just used to hitting a button on a panel and then making a connection. And you'll see some of that kind of stuff over in the process. So that's one area where it's gradually evolving at this moment in time, but not all devices support that. But that would really simplify entering IP addresses. So the interop, we have hundreds of devices, and at each particular location, we get a large spreadsheet that we have to enter all these values in order to connect to each different device. So that's one of the real challenges at the moment.
Yeah, I heard about a OB van that had 500,000 multicast addresses to configure. So that was a big spreadsheet.
Right, yes.
Any other questions? Anybody else?
Second part to that question was the test equipment that might be coming down the road.
Okay, so we have a device called Prism, which allows us to monitor the IP stream today, and that'll monitor it for 2022-6 and 2110. We're gradually evolving the measurement processes like I've shown here. All of those are available today to basically measure the stream. There's still more work to be done on identifying and simplifying some of those processes, but that's what we have today to basically monitor the signals.
How much is the Prism?
So the Prism starts at about $15,000, and then depending on configurations and options, it goes to about $25,000. So it does both SDI and IP, about $15,000.
Okay. Well, thank you very much, Mike.
Thank you very much.